So though I mean the chapter in general is called simple harmonic motion, but it includes also angular harmonic motion, and later we will also include damped oscillations in this. So we were discussing about angular harmonic motions, and we saw the case of the this thing, the torsional pendulum. The last thing, it's a direct formula based thing, nothing else in torsional pendulum. Now we'll see another type of pendulum, which is called a spring pendulum. This is the type of pendulum, for example, that is the working principle for mechanical wristwatches. You know, before electronic wristwatches driven by electronics came into the picture. So you had, I'm not even sure whether people in your generation would have seen these, but the mechanical wristwatches, which one variety of them actually needed to be winded every day, like you wind a grandfather clock, so to store potential energy in it. But there were more varieties which were able to store energy on the basis. Yeah, I will send the recording and the notes also, Tanish, of the last lecture. So there were also other varieties which were like refined models of mechanical clocks, wristwatches, which use the movement of your wrist in daily life to store kinetic energy, and that kinetic energy would convert to potential energy. So you would not need to wind the watch. And of course, it does not have any electrical power source because it works completely on mechanical principle of pendulums inside or oscillators inside. Very interesting engineering behind these things. Anyhow, so let's look at spring pendulum. The most basic example of one would be something like this. If you have like a thin rod, okay, which is on a smooth horizontal surface. So gravity is going into the plane here. Gravity is not playing a role in the motion at all. Okay. So this is a thin uniform rod on a smooth horizontal surface. So mg is into the plane, normal reaction is coming out of the plane of the diagram, they're balancing each other. And it's hinged over here. And in the simplest variety, we would just attach one spring, but we can attach any combination of springs also. There's an ideal massless kind of spring attached anywhere, actually it could be, but I have attached it at the end, such that at the natural length position, the spring is actually perpendicular in its orientation with respect to the rod. Okay. So this is at the natural length position. So first of all, we will show that for small oscillations, and by small we mean small amplitude oscillations. So that means small angular amplitude or angular displacement, whatever. The rod will perform angular harmonic motion. And we'll find the time period. So straight away from what we've written down over here, you can understand that there is some kind of application of small angle approximation when we look at the displaced position from equilibrium. Okay, so let's visualize this rod now given a small angular displacement. So although in the diagram I'll show it like it's a significant angular displacement, but you just imagine that it's an angular displacement which is definitely less than 5 degrees, so that don't have too much problem with the application of small angle approximations. So anyhow, so if we do that, now imagine that this is actually a small displacement. So this is going to remain more or less along the same line that it was, only it is getting stretched. Actually, it will get slightly bent like this, okay, but because we are taking theta to be small, the angular displacement theta small. So this becomes L plus X, okay. And as you can see, this applies more or less a restorative torque, that tension, okay. So The length of the rod is L here. You can see the moment arm for that tension is the base, which is L cos theta. So it's producing a restorative torque like this. Therefore, an angular acceleration like this.
There will be hinge reaction also.
Sorry, there will be
hinge reaction.
Hinge reaction force will be there, but that will not be producing torque, na beta. So this is like a pure rotation. So when we solve the torque is equal to I alpha equation about the axis of rotation, okay, so we don't need to include the hinge reaction force in that, right? Because it does not produce. So there is actually a number of forces. There's hinge reaction force, like you said. There is mg and normal reaction also. But both those forces are perpendicular to the plane of the diagram and they are balancing each other. So they won't be producing any torque. Like mg is going into the plane. So it's creating a different sort of torque.
Yes, sir.
That torque is such that, you know, the unit vector for that torque will be actually like this. Now it's going into the plane. So the unit vector will be like this. It will be along this kind of axis like this. But then normal reaction is coming out. So its unit vector will be opposite. So as vectors, they cancel each other. So the net torque because of mg and normal reaction balance each other. The net torque because of the reaction force at the hinge is 0. And therefore, the overall net torque is only the torque produced by this tension. And the tension is, of course, kx in magnitude.
Okay, sir.
Yes.
So we have this producing tension. So kx, so this is about the hinge. Okay. Let's say the hinge is the point O. So about the hinge at the point O. Okay, so kx is the magnitude of the tension. Okay, and the moment arm, as you can see, will be this perpendicular distance because this line of action, the tension or kx's line of action is this line. So its perpendicular distance is this one. So that is L cos theta, right? So this is the torque, and this should be equal to ml square by 3, being a thin rod and all that, alpha. And in this case, again, alpha is negative of d2 theta by dt square because of that sense of it being opposite. It's restorative. Okay. Now comes in the small angle approximation. So theta is small. So what we can see here is that cos theta we will approximate as 1, and x we will approximate as L theta, because you know you can understand that the rod is rotated through an angle theta like this. So this is basically what we are taking as x, whereas this is the arc length. So the rod's length is L. Angle is equal to arc upon radius, whereas sine theta is x by L. And for small angle, theta will become approximately sine theta. So the arc length becomes approximately equal to x like that, L theta. Like that. So that's how this approximation comes. Okay. So putting these approximations in the above equation, we get k into L theta into L becomes approximately equal to ml square by 3 into minus of d2 theta by dt. So we got the angular harmonic equation and we got the value of omega square. So that thing is done. We got the time periods formula directly from there. It will be 3k by m, the minus sign, into theta. So omega square is 3k by m. So there you go. The time period is 2 pi under root square root of m by 3.
Sir?
Yes.
But in this case, sir, theta will be like prominent, na sir. It will not be ekdam chota sa.
Theta should be small only, beta. Because if theta is large, like actually in my diagram, theta is large. You have to imagine it's small. So in such a diagram, the actual spring would have gone from this kind of position here, would have gone into this kind of position here. You understand the point? This would be the situation of a large theta.
So it's like a very small SHM, right? It's going.
Yeah. Yes, it's a small amplitude as harmonic motion.
Yeah.
It's a small amplitude angular harmonic motion, isn't it?
Yeah.
Okay. So the thing is, like, even if you give it a large amplitude, it will still oscillate because there is no non-conservative force and there is restorative force. But that oscillation will not be harmonic in nature because this relation will not hold, that your alpha is proportional to theta in magnitude.
Yes, sir.
There will be some other complex relation, like it will be a complicated relation of sine theta, cos theta, everything put in there.
Yes.
Only when theta is small, we can simplify that relationship to direct proportionality to theta.
Yes.
So that is the key thing in these type of questions. You have to be able to do the approximation so that you can come down to that simple relation that d2 theta by dt square is minus omega square theta. Or in case of SHM, d2 x by dt square is minus omega square x.
Yes.
Okay, so just the final thing from here, you can see omega square for the angular harmonic motion. So notice it comes in the same form like a spring mass system. If you have just a simple spring mass horizontal system, the formula was square root of m by 3k into 2 pi. Here it's sorry, m by k into 2 pi. Here it is m by 3k. That factor of 3 is coming because moment of inertia is involved and all that, but it has the same dimensions and it depends again on the inertia of the block. In this case, the inertia of the rod, the mass, and the elasticity of the spring. It is k. Yes, Samar, that is correct. If you change the position of the hinge, for example, if you change it from the one end to the center of mass position, then both in the torque equation, the moment arm will change, as well as on the other side of the equation, torque is equal to I alpha, the value of moment of inertia will change. So the whole formula of time period will change. But again, it will be of the type 2 pi into square root of some numerical factor into m by k. Here, that numerical factor is 1 by 3 because of that geometry. Okay. Similarly, if you replace the rod with some other kind of object, if it's a cylinder for that matter or something like that, accordingly these things can change.
So omega is 3k by m, no?
Yes, yes, 3k by m. Omega square is the coefficient of theta in that equation which is in the box. Samarth, if the rod is not hinged, then it is not capable of oscillating only, na, beta, because there will not be any stable equilibrium position. We just attach one spring from one end like this. Now, unless you place it like this, then you place the rod like this. The rod is like this and the spring is lengthwise and it's on a smooth horizontal surface. So then yes, it can do a linear SHM if you give it a displacement along that line only. But if you place a rod this way and the spring is this way, and then you give it a displacement, and of course you're attaching the spring. If you don't attach the spring also, then of course it will not make any difference at all on a smooth surface. But then it will be a very complicated type of motion. It will not be an oscillation at all.
Okay.
Hope you're understanding the point. So in any case, here we are discussing a specific situation which is called the spring pendulum. So any pendulum will always be an angular harmonic motion with a fixed axis. So it has to be that situation. By definition, a pendulum has to be in that way. Okay, now let's look at, so now any sort of variation of this can come into play. For example, you have a very simple variation of this where you have a solid disc which is hinged at the center and again on a smooth horizontal surface. So it's a disc, uniform thin disc of mass m, radius r on a smooth horizontal surface. And hinged about a vertical axis, fixed vertical axis at O. So just this disk alone, if you give it some angular speed, it will just keep rotating forever with omega because there's going to be no torque. But now suppose we attach a spring over here such that when the spring's orientation is like this, it's at natural length. And let's just say for argument, we attach another spring here. So both the springs right now are in natural length position. This is the equilibrium position. So both the springs are along the tangent to the disk at diametrically opposite points like this. So again, find the time period of angular harmonic motion. For small amplitudes. Or in simple terms, this kind of thing is just called small oscillations. The term small oscillations means oscillations with small amplitude. It can be linear, it can be angular, it doesn't really matter. The term small oscillations covers all that. So basically you have to again work out from the dynamics that if you give it a small angular displacement about the hinge, it will have the condition for angular harmonic motion. And from that condition, you find out the value of omega square and from that the time period. So these are those very quick fire type of questions. It should not take you very long to figure this out. This is like a JEE Mains single option MCQ level question. Anybody got the answer? Just make a free body diagram where you have given a slight angular displacement
Yes,
about
1 minute.
that. Yeah. So that vertical dotted line that I've drawn, actually it's not vertical. Vertical is coming out of the plate, but that vertical and that diameter that I've drawn joining the 2 points through O, where the springs are attached. Just imagine that has rotated by small angle theta. So how the springs will apply restorative torque? Use that concept.
Sir. Sir.
Yes.
Sir, is it rotating or is it going up and down?
But it's got a fixed axis na, at O. So it cannot go up and down. Na?
Fixed hai. Okay.
It's a fixed vertical axis at O and it's on a smooth horizontal plane. You understanding the point? Na?
Yes, sir.
Yeah. So that fixed axle will not allow you to displace it that way. Its center of mass cannot move. It can only rotate about the center of mass. Okay, Devansh, very good. That's correct. Your answer for time period is correct. So what we'll realize here that whether you give it a clockwise or anti-clockwise rotation or angular displacement, there's not going to be, there's going to be restorative torque. Okay. So for example, if we were to rotate this anti-clockwise to an angle theta, then both the springs would get extended. So this one would also get extended. This one would also get extended.
R theta.
Yeah, and for small angle, yes, you could treat the x as r theta. So the tension that is acting inwards like this for small theta, x would be r theta. Okay. And r cos theta would be approximately equal to r. So 2 times tension into r cos theta. That would be a net torque. That would be equal to mr square by 2 alpha. This is our torque is equal to I alpha equation. These would produce an alpha that would be like this. Or similarly, if you give it a rotation like this over here, and both of them would get compressed. Both the springs would get compressed and apply an outward sort of
Yes, sir.
force. So tension would be like this in both these cases. So both of them would generate the same equation. Only the sense of, so this is L minus X then. So you can use the common equation for both the sides. In all cases of oscillations, there is symmetry on either side displacement. So, okay, so this would now become 2 times kx r cos theta is equal to mr square by 2 alpha, where alpha would be minus d2 theta by dt square. And you bring in the small angle approximation. So for small angle, you have 2 times k r square theta is equal to mr square by 2. So we have the relation. That's your angular harmonic motion.
Yes, sir.
Yes.
सर अगर cos theta is equal to here तो पहले से हम लोग r theta ले सकते थे, right?
Yes, yes. मतलब थीटा स्मॉल है ना, तो पहले से उसको r थीटा ले लो, x को r थीटा ले लो और cos थीटा को 1 ले लो.
Assume it previously that theta is
like when you're doing an objective question, you can just directly write the torque. When you're writing this step only, you can just write it as 2 times k r theta into momentum, which is r.
Yes.
That is equal to mr square.
Yes.
Okay, so this becomes a formula for time period. Yes, Durgesh, that's correct. So this is like effectively it's a one-line solution, as you can see. Now from this diagram, you can just see, you can directly write this. Okay. H.C. Verma exercise does not have any problems of spring pendulums. It has problems up to that torsional pendulum, and of course physical pendulum. It has some good problems based on physical pendulum. It does not have damped oscillation problems also, H.C. Verma. So you'll have to rely on your module for those things. Okay. Damped oscillation is also there in a lot of detail in NCRT. But what is there in your module is more than enough for your theory-wise part of damped oscillation.
So for practice, we do H.C. Verma.
You do H.C. Verma for all the, I mean, you do all the questions of H.C. Verma, but remember H.C. Verma does not cover questions of spring pendulum and of damped oscillation. So you need to cover those questions from the module.
Okay, sir. Okay.
Okay, so this covers the regular types of SHM and all the various standard types of questions. Now there are some more situations in which SHM happens, so we'll discuss them one by one. So one important situation is SHM of a floating object. If an object is floating in water and in liquid, and you either pull it out or you depress it further and release it, it bobs up and down. Just imagine a wooden block floating in water, and let's say you apply some impulse or you just push it down and release it from a displaced position, or even pull it up vertically up from the equilibrium position, not completely outside, okay, but just above its equilibrium position and release it, you will see it performs oscillation, it goes up and down. Okay, so that oscillation is an SHM we can prove. But of course, for that, we are assuming that we are treating water or whatever liquid in such a way that we can neglect the viscous force that acts between the surface sorry, not the viscous force, the surface tensional force. That is the cohesive force and adhesive force, those things. We can ignore the surface tensional force between the floating object and the liquid. And we are considering only the buoyancy. Okay, so SHM of a floating body. So this proof that it's an SHM and the formula for time period and all, it is a bit conditional. It is an idealized situation. Practically, it's not going to be that. Okay, practically again, it's going to be a damped oscillation because there is a non-conservative force of surface tension and viscosity and all that involved. Okay, so this is assuming the absence of drag forces, that is viscosity and surface tension. So practically, it's not that you can neglect, I mean, you cannot assume they're absent, but if they're small enough to be negligible, then it is almost a perfect SHM. It will, over a period of time, it will dampen, okay, but it will have very large number of oscillations before it significantly dampens. So imagine like a wooden block or something, solid wooden block. Now, suppose initially it is in equilibrium in water, such that let's say 60% of its volume is submerged. So it's at rest in static equilibrium with 60% of volume submerged. Now we'll show that if you depress this slightly or if you pull it out slightly and release it, it performs SHM and we'll find the time period. So this side length is L and this area is E. So the volume of the block, so there's an example of this. Okay, the volume of the block is E into L. Okay, and density of wood, let's say, okay, now it's given that it's in equilibrium, at equilibrium initially with 0.6 part of its volume submerged. So we will assume the standard density of water So the volume of the wooden block is this much, density of wood is so much, and let's say mass of the wooden block is 6 kg, and acceleration due to gravity is 10 meters per second square. Okay, so if the block is pushed down slightly and released, by, let's say, a vertical displacement of, let's say, L by 10 and released, find its time period of SHM. Okay, so first of all, actually, what you do is before you find the time period, you prove that, show that it will perform vertical SHM. Now I'll give you the hint of how to do this proof. So you can see that at this given equilibrium position, buoyancy is balancing the weight. So naturally, if you take it below the equilibrium position, your buoyancy is increasing, upthrust is increasing, weight obviously does not change. So there's going to be a net force upwards. So downward displacement results in upward acceleration. Similarly, if it was above the equilibrium position, your submerged parts volume is decreasing. So buoyant force will decrease, whereas weight remains invariant. So this time that net force will be downwards. Okay. So whether you bring it vertically above equilibrium or you take it vertically below equilibrium, either way, there's going to be a net restorative force, because one of the two forces dominates over the other, and that points it in the restorative direction. So that's what shows you that the system is capable of oscillating. Now, what you have to prove is that that restorative force is directly proportional to the amount of displacement. So that is where, to prove that, you will have to make the FPD and show that the net force or the acceleration, whatever, is directly proportional to the amount of displacement and opposite in direction. From that, you will get the proof that it is SHM, and directly from that same equation, you will get the value of omega square of the SHM and time period, etc. In this case, we will also write the equation of SHM. That means we'll need the time period and phase constant also. Okay, so what we will do is we will compare the equilibrium condition with, it's actually very easy. So we can compare it alongside with both the situations when it is above equilibrium as well as when it is below equilibrium. This is the above position, let's say, and this is the below equilibrium position. Let's say this is the water level. So this is equilibrium position, or what in SHM language we will call the mean position. Then compared to that, this one is where there is a vertically upward displacement of y, let's say, and correspondingly there's a downward acceleration of a. Whereas this is one where there is a vertically downward displacement of y. So there's a vertically upward acceleration of a. So the equilibrium state, this part is 0.6 L because it was given to us that 60% is submerged. Okay. And the buoyant force balances mg. So density of water into 0.6 L into A balances density of wood into L into A. So you can see that density of wood, this is an understood fact. Okay. Now here what is happening is that the buoyant force is becoming less. B is less than B naught. So mg will dominate and it will have a downward acceleration. So mg minus the new value of buoyant force will be ma, and the new value of buoyant force will be density of wood into 0.6 L minus y, because this length now has become 0.6 L minus y to A into G. This total thing is our buoyant force. This is equal to ma. So now compare these two equations and you can see that this factor will cancel out and we are left with this factor. So this whole factor will become 0 when you compare with this equation. Similarly, in this case, you can see buoyant force would have become more. If the buoyant force is B prime here, B prime has become greater than mg. Sorry, greater than B naught. Yeah, and therefore greater than mg also, but more importantly, greater than. So for this one, what is happening is that and B prime is density of wood into 0.6 L plus y, because it's submerged further. Okay. So this equation will become like this: 0.6 L plus y into E into density of wood minus mg is equal to ma. So both these equations, when you substitute this information here, both these equations will give you the same, that density of wood into A into G into Y is equal to ma. and A is in either case d2y by dt square with the minus sign. So you have your SHM equation. Now you have to just be able to express the value of time period and omega square. Just note this down and try to complete this problem yourself. It's quite simple, as you can see. From here onwards, you have to just substitute correctly.
Sir,
Yes, very good, Samar. That's correct. So we will get formula ultimately that looks very much like the simple pendulum's formula, but with a relative density term also. Though it's nothing like simple pendulum actually. That is an angular harmonic motion. This is a simple harmonic motion. Okay, but nonetheless, so M we can write as density of. Oh, sorry, I've made a mistake. This should be density of water. No? This side. This is density of water. Please make a correction. This is density of water. So is this term. And so is this term here also. Probably the same thing I have to do here also. Yes. Please note this correction here. This is density of water all the way here. On the other side, the mass of the wood we can write as density of wood into the total volume. So as you can see, A, which is minus d2y by dt square, comes out to be density of water divided by density of wood into G by L. This whole factor into Y. So this is our equation of SHM. This kind of term. Okay, so omega square is G by 0.6 L. You can write like this, or density of water divided by density of wood into G by L. So time period is 2 pi under root 0.6 L by G, or it is 2 pi under root that relative density of wood factor 12 by G. In this case, we can't find the value of L, I mean T in seconds, because L was not given to us. But suppose it was given in that sense. So let's take a situation where actually the mass was given, but because neither I've given the area nor the L, let's say I've given the value of L, it is 50 centimeters. In this case, this will become like this, right? The time period will become. Okay, now also if I take the y-axis upwards, okay, then my initial displacement would have been minus L by 10 because I had depressed it down by, so it would have been minus 5 centimeters, and my initial velocity would have been 0. So I would have got the equation of SHM like this, that y is equal to a sine omega t plus phi, where omega we have got but the value of amplitude is okay, and the phase constant be in this case minus pi by 2. It's tan inverse of an undefined quantity division by 0. But here the initial position you can see is negative. So the phase constant should be such that, this tells us that sine phi should be negative and cos phi should be 0. That thing we had discussed earlier on in the kinematics of SHM. That thing becomes important here. So the phase constant would be minus pi by 2 instead of plus pi by 2. So the equation of the SHM would be like this. Y equal to A sine omega t minus pi by 2, or minus A cos omega t. Starts from negative of A, where the amplitude we have written now 5 centimeters or L by 10, this part, and omega is this much. So we know omega and amplitude. I mean, omega, amplitude, and phase constant, all three are solved. So we have the complete equation of SHM. Okay, so it's all mechanics at the end of the day. It's just you have to be able to solve the dynamics or work energy equation, whichever you're opting for. In such a case, you'll always go for dynamics. Okay. So you'll have to solve that up to a point where you reach the standard equation of SHM or angular harmonic motion, whichever be the case. And from there, you compare it with the various formulae that we've learned. Okay. Okay, so people hope this is clear. So this is one of the variations of SHM that I was talking about. Okay. Now we move on to another interesting variation of SHM, where we will look at the concept of something called reduced mass. Okay. So SHM for a system about its center of mass, while the center of mass itself is in motion with respect to the ground frame. That kind of situation, very interesting. Okay. So mostly this is like spring mass systems we're talking about. But we'll also talk about a few cases of pendulum systems where this can be happening. So example one of this is a type of system which we have done a lot of analysis from center of mass perspective in terms of velocity of center of mass and things like that. But we have not really done anything from time period and oscillation part yet, which is where today's lecture comes in. So let's say we have a system of two blocks on a smooth surface that are initially in equilibrium with a ideal massless spring in the relaxed state joining them. So this system is initially at rest. So let's do it with an example where we know the masses also. So M1 is 6 kg, suppose M2 is 3 kilograms. The spring constant is 8 newtons per centimeter. Now the system is initially at rest in equilibrium. The smooth floor. Now a sharp impulse acts on this block horizontally at time t equal to 0. It could be from another collision occurring, or somebody hits it with a stick or something like that, or just punches this block. So large amount of force acting for a short duration of time. So a impact impulse kind of thing. So a sharp impulse J acts on M1 at time t equal to 0 as shown. So show that the blocks will oscillate in SHM with respect to the system's center of mass, not in ground frame, because the center of mass will be moving. Okay, and find equation of SHM, time period, maximum extension, compression of the spring, okay, maximum speed for each block, etc. All these things we have to find out. Okay. Now, given also that the magnitude of this impulse that we are applying is, let us say, 0.72 Newton seconds. So as I said, we would have seen questions like this in center of mass, where we are calculating maximum compression, maximum extension, maximum speed of each of the blocks and all this. But this whole business of showing that it's an SHM and finding the time period, this is where this chapter's analysis comes in. Okay. So just take down the data of the question first, the values of the masses, how the impulse is acting, the diagram and all that, then we'll discuss. Okay, so let's go about systematically solving this problem. So first of all, let us understand what is the state of the system at t equal to 0 just after the application of the impulse. We just finished applying that impact impulse, or that collision impulse. So what has happened is, because the spring was in relaxed state, there's no part of the impulse has acted on the second block. It's only acted on the first block. So the first block develops an initial velocity 1, whereas the second block remains at rest. At that moment, the spring remains at natural length at that moment, but the center of mass of the system, it develops a velocity. So this is the situation at t equal to 0, just after the impulse J was applied. Immediately at that time, this is what happens. So you can see, by applying impulse momentum, J is equal to m1 u1. So here we will get 0.72 is equal to 6 u1. So u1 will come out to be 0.12 meters per second, or 12 centimeters per second. So u1 is this one, this much, and therefore VCM will become m1 u1 divided by m1 plus m2. This is at t equal to 0. So our VCM will be 2/3 of this. You'll see, be 6 upon 6 plus 3. So that's 2/3 of 8 centimeters per second. Okay. So all this was given to us. All this information given. Now, if we compare this with after some time, what has happened to the system? So first of all, we'll understand that there is no net force acting on the, there's no net external force acting on the system. There's no acceleration of the center of mass. That's a very important point. So from this point onwards, whatever happens to the system, the center of mass will have a uniform motion. So the center of mass frame for us will be an inertial frame. So when it comes down to proving the SHM of each of the blocks and all that, with respect to the center of mass, we'll still have to work with Newton's laws in inertial frame only. Okay. So here also the center of mass is traveling with a uniform velocity. Acceleration of the center of mass is 0. But by now, let's say this one's velocity has become v1. This one's velocity has become v2, because the spring has compressed. Okay. So this one is having an acceleration a1. This one is having an acceleration a2. And this I'm analyzing at some time t, but from the ground frame point of view. So the important thing to understand here is that the center of mass will move at uniform VCM from t equal to 0 onwards, because there's no external force on the system. The net external force on the system is 0. So next, what we will do is we will make the FBDs of each of the blocks in the center of mass frame, keeping in mind that it's a inertial frame only.
Okay, sir.
Okay, so hope the first diagram was clear after the question, that is this one. Okay, where at some time t, the spring has got compressed by x, and therefore the block M1 is in the process of deceleration, is velocity some v1 in the ground frame, and the block M2 is in a process of acceleration because the spring is compressed, so it's pushing M2. So that diagram now we have to analyze the free body diagram of M1 and M2, but not in the ground frame, in the center of mass frame, so that we can show that in the center of mass frame it has performed, they are performing the SHM motion. Okay, so hope the question is clear. I'm coming back to this now. So what we have to do is now, these two diagrams that we have drawn, they are in the ground frame. Here our observer is the inertial observer who's fixed to the ground. Now next what we'll do is we will observe this situation again, but from the center of mass frame. So assume our observer is running at a constant speed of whatever that is, 8 centimeters per second along with the center of mass. So what he sees, oh, direction of V2, my mistake. Direction of V2 is the same as direction of this thing. It's accelerating, not decelerating. Yeah. Please note that correction. V2 is the same direction as V1. Yes, Shikha. So yeah, so at this stage, what is happening is the block M1 is decelerating, whereas the block M2 is accelerating. So next, to prove that SHM thing, what we'll do is we'll make these two FBDs. The motion of the blocks in the center of mass frame. We'll view it from that point of view. The earlier one was in the ground frame. Now, mind you, the center of mass is moving with uniform velocity. So it is an inertial frame. This velocity it is moving with, which we had worked out to be 8 centimeters per second earlier. Its acceleration is 0. So therefore, the center of mass frame is an inertial frame. It is not a non-inertial frame. For pseudo force and non-inertial frame, the frame should have non-zero acceleration with respect to the ground. Remember that thing? Okay. So now our observer, just imagine he's running along with the center of mass. So this is the center of mass frame, which is an inertial frame, though it's not a stationary frame with respect to ground. So in this frame, suppose at t equal to 0, the blocks were here and here. One block was here. One block was here. M1 and M2, they were here at t equal to 0. And this whole distance is the natural length of the spring. So in that frame now you'll understand using relative motion concept that the velocity of block 1 with respect to center of mass is velocity of block 1 minus velocity of center of mass. Okay, so by that logic you can see that u1, that is the initial velocity of block 1 with respect to center of mass, is u1 minus bcm. So u1 was plus 12 centimeters per second and vcm was 8 centimeters per second. So this is plus 4 centimeters per second. So the initial velocity of the first block with respect to center of mass, which is what we are seeing in this case, is this. This is moving at 4 centimeters per second and its acceleration will be 0. at that moment because x is 0. So there is no net force on this block. Okay. Whereas initial velocity of block 2 with respect to center of mass is initial velocity of block 2 in ground frame minus velocity of center of mass. So the block 2 in ground frame was at rest. The center of mass is moving at 8 centimeters per second. So it's minus 8 centimeters per second. So at t equal to 0 time, this guy is moving towards the center of mass at a speed of 8 centimeters per second. And its mass is 3 kg. Moving at 6 centimeters per second. So 6 kg. And its speed is 4 centimeters per second. And this one, the acceleration is also 0. So what happens at time t? The spring is compressed by x. So both the blocks have respectively come closer to the center of mass. The guy in the center of mass frame, this is what he sees. That at time t, this has come here, this has come here. And by now the whole spring has got compressed by x. So this has changed to L minus x. So as the spring has got compressed by x, there is net force acting on each block in this frame. So in general, this is having an acceleration in this direction, this is having an acceleration in this direction at this time. So this is what is happening. Okay, so now let's say that this block's displacement from 0 to t has been this much. Okay, this block's displacement in this much, and this block's displacement has been this much. So this is x2, this is x1. So also we can see over here that the total compression of the spring is equal to x1 plus x2, because the distance between the blocks has changed from L to L minus x. So one block has come closer to the center of mass by x1, the other has come closer by x2. So x, the total reduction in the distance between them, the total compression of the spring is the sum of their individual displacements with respect to center of mass. So one thing you have to understand here is that x1 and x2 are displacements with respect to center of mass. Okay. Then again, a1 and a2 that I've shown at time t, their acceleration with respect to center of mass, the center of mass frame. And x is the compression of the spring. At time t. This situation. Okay. So what does the free body equation of each of them tell me? So from FBD at time t equal to t of block M1, what we see is that Kx is equal to M1 A1. Okay. And A1 is minus of d2x1 by dt square. And from the FBD of block M2, we see that Kx is equal to M2 A2 and A2 is equal to minus d2x2 by dt square. So we've not got the equation of SHM yet, because you can see that A1 and A2 are related with x. They're not related with x1 and x2. That is where we'll have to use the center of mass concept and the constraint relation number 1 that we've written. Okay. So This is like a constraint relation that the net compression of the spring is the sum of their displacements. This is our first dynamical equation, F is equal to ma type equation. This is our second dynamical equation. So now the dynamics equations have to be converted in such a way that we can show that they are SHM. That means A1 should be related with X1 instead of X, and A2 should also be related with X2 instead of X. So that is where we'll bring in the center of mass concept. But first, just make sure you understood up to this step carefully. Okay, so if you are in the center of mass frame, you are running along with the center of mass, then you will see both the blocks M1 and M2 moving towards the center of mass in that time t. And the spring's length is getting lesser. It's gone from L to L minus X because M1 has moved towards the center of mass by a distance X1, and M2 has in turn moved towards the center of mass by a distance X2. So they are moving in opposite directions, coming towards the center of mass. While at the same time, the spring is pushing both of them outwards. So their accelerations are opposite to their direction of displacements. So they're already fulfilling the criterion of oscillation, that they have restorative force. Now, the only thing is you have to show that that restorative force is proportional to displacement. So then you get the equation of SHM. That is the approach in everything to do with SHM actually. Okay, so Jagannath, if you're finished with this part, then we'll come to the relationship between X, X1, and X2 once more, so that we can get the equation of SHM. Okay, so hope this part is clear. Yes.
Sir, in the FBD part, it will be Kx1 equal to M1A1, right?
No, beta. So that is the point. Now, who is applying the force on the block? Is the spring, no? So spring ka state kya hai? It is compressed by X, no? It's not compressed by X1 or X2. You understanding the point, no?
Yes, sir.
Okay, so the tension in the spring, that is the force that is acting, that is equal to kx.
Yes.
Okay. But at the same time, what we will see next is that x itself is proportional to x1 or x2. So using equation 1 and also using the fact that m1 x1 is equal to m2 x2. How we know this? Because x1 and x2 are displacements in the center of mass frame. No? Okay. So in the center of mass frame, displacement of the center of mass is 0. Okay. So summation of m into s in that frame must be 0. No? Okay. So basically vector sum of m1 s1 plus m2 s2 must be 0 in the center of mass frame. So therefore m1 x1 minus m2 x2, you write as a scalar, should be 0. Okay. So this is an additional equation that I have now. Yes. So if you look at solving, so we have relation that x1 is to x2 is equal to m2 is to m1, which in this case is 1 is to 2 because of the masses given. And from equation 1, x1 plus x2 is equal to x. So if I solve this as a system of simultaneous equations, you can see now that x1 will become m2 upon m1 plus m2 times x, or in this particular case, it will become 1/3 of x, and x2 will become m1 upon m1 plus m2 x. So in this particular case, it will be 2/3 of x. To the right of the free body diagram, Jagannath, we've just written the values of which are given in the question and the definition of center of mass, relative motion. These are relative motion equations. Okay. Initial velocities in the center of mass. That's illustrated in the diagram also. Okay. So anyhow, you can pick it up from the recording later if you got disconnected. I'll send you the recording very soon. Okay. So now let's concentrate on these two equations. So now substitute this in equation 2. So write x as m1 plus m2 upon m2 times x1. Substitute in equation 2 this thing. So equation 2 becomes that k into m1 plus m2 upon m2 x1 is equal to m1 a1, and a1 is minus d2 x1 by dt square. So we have the equation of SHM, that d2 x1 by dt square is minus of k into this term m1 plus m2 upon m1 m2 times x1. So this is an SHM equation, you can see. So individually this shows that block 1 is performing. S is displacement beta in general. So that's a general equation that I've written, center of mass equations. So this is general formula for displacement of center of mass, and this is the application of it in this case. So this is how it is applied over here. Okay, that's why I've written it in brackets, because it's a reference to something you learned earlier. So this is SHM of block M1 in the center of mass frame. Similarly, we'll show SHM of block M2 also, but first of all, this gives us omega square for the SHM. Okay, so this is basically showing us that x1 will be some amplitude, let's say a1 into sine omega t plus some phase constant phi1, where that omega is such that omega square is this term km1 plus m2 upon m1 m2. So when you work this out, you will see this is 800 newtons per meter into 6 plus 3 divided by 6 into 3 in kgs. So omega square will come out to be 400. So omega is 20 radians per second. Okay. I'll come to A1 and A2 also. But before that, now you substitute. We'll just take another 2 minutes. So substitute this in equation 2 above. Okay. So x is equal to m1 plus m2 upon m1 this time into x1. Sorry, into x2. Substitute this in equation 2. So equation 2 becomes kx, that is k into this is equal to m2a2, where a2 is minus d2x2 by dt square. So you are again getting that same thing, that d2x2 by dt square, if you can see the same term minus k into m1 plus m2 divided by m1 m2 into x2. But okay, so this is like a symmetric equation for the SHM of the second block, SHM of block M2 in the center of mass frame. So this shows us now that x2 will be some amplitude, let's say a2, but into sine of the same omega t plus some phase constant phi2, where this omega is the same. Now for finding a1, a2 and phi1, phi2, we have to use the initial conditions, which is also going to be very similar in process. Okay. So in this, we have to now find what is a1 and phi1. And in this, we have to find what is a2 and phi2. Once we do that, the problem is complete. Okay. So for this, we can see that x1's initial value, that is at t equal to 0, the value of x1, which should be a1 sine phi1, is 0. Whereas its initial velocity, you'll remember, was it was 4 centimeters per second. So that is our a omega cos phi. That was equal to 4 centimeters per second. So I'll just refer you to the diagram to remind you of that. Okay. In the above diagram, you can see that at t equal to 0, they're both starting from 0 acceleration. So they're starting from the mean position. Okay, but with velocities of 4 centimeters per second, and this one is 8 centimeters per second. So keep that diagram in mind while writing these initial conditions. And from the initial conditions, you can see that a1 will be square root of x1's initial value square plus b1's initial value square by omega square. So in this case, this amplitude will come out to be 4 centimeters per second divided by 20 radians per second. Okay. Because x1 is 0. So this one will come out to be 1 by 5 or 0.2 centimeters. And phi1 will come out to be pi by 2, because cos phi is positive and sin phi is 0. Now, by similar treatment, you will see
Sir.
here. Yes.
Sir, won't it be 0?
Which one, Vida?
Phi 1.
Oh, yeah, sorry, my mistake. Phi1 will be 0 because sine is 0 and cos is positive. No? So it will be, yes, that's correct. Phi1 will be 0. So just make that correction, everybody. Okay, now by similar logic here, you can see x2's initial value is 0, but v2's initial value in the diagram you had seen was 8 centimeters per second. So once again, from this you can see that a2 sine phi is 0 and a2 omega cos phi is 8 centimeters per second. So our amplitude is 0 square plus 8 centimeters per second divided by 20 radians per second whole square. This amplitude will come out to be 0.4 centimeters. And the phase constant by same logic will come out to be again 0. So now I know the complete story that A2 as a function of time is 0.4 sine 20t. And A1 as a function of time, sorry, not A1 and A2, but x2 and x1. A1 and A2 are the amplitudes. Okay, so this is x2 as a function of time. And from here, x1 as a function of time is 0.2 sine 20t as a function of time. When each of these x1 and x2 are in centimeters, time is in seconds. So they are individually doing SHM with omega this much and time period this much. Okay, and also the state of the spring, remember that was x1 plus x2. So that's also becoming very simple. It is 0.6 sine 20t. So the spring is also, doing its oscillation with an omega or a time period of 2 pi by omega or pi by 10 or 0.314 seconds. Okay, and that also shows you that the maximum extension or compression of the spring is equal to 0.6 centimeters. When x is plus 0.6, you are at the maximum extension state, sorry, maximum compression state, because x has shown as the compression. Whereas when x will be minus 0.6, it will be the maximum compression, maximum extension. Because if I've taken x as a compression, then negative x actually means extension. So the spring keeps oscillating between, natural length to maximum compression of 0.6, back to natural length to extension of 0.6, back to natural length. And while the spring is doing that, if you're running along with the center of mass, you will see the first block oscillating with an amplitude of 0.2 centimeters, the second block oscillating with an amplitude of 0.4 centimeters. Okay, so we will conclude today's session over here. So this is like advanced kind of application of simple harmonic motion, where SHM is happening in a system where the center of mass is moving and multiple blocks or multiple parts of the system are doing SHM in that center of mass frame. Okay, so we will come to a couple of more examples of this and discuss about that also in the next lecture, along with more questions and of course damped oscillations. Damped oscillations, you actually don't need to worry about this stage. It's just a formula and a theory kind of thing, which will just take a few minutes. What we have to concentrate is in doing questions of SHM, which involve a lot of mechanics applications. Like in this one, you can see there's application of center of mass concepts. In previous lecture, we've seen examples where rotational mechanics, rolling concepts are used, or spring constraint concepts are used, or rotating pulley constraints are used and all that. So essentially, it's like your entire core mechanics concepts can come into application. Okay, so that's it for today's session, people. Wish you all the best, and we'll pick it up. We have one more lecture this week, so we'll complete everything in that lecture.
Thank you, sir. Bye, sir.
Thank you, sir.
Thank you, sir. Bye, sir.
Okay.
Thank you,
Bye.
sir.
Bye.
Thank you, sir. Bye.